all of its science data down in a part of the spectrum we call K-band, so a shorter wavelength, so we have a higher data rate. And we telemeter down at about 4 megabits per second to one of 3 deep space network ground stations that are across the Earth. There's one in Spain, one in California, and one in Australia. So we'll be using the 34-meter antennas at these facilities to bring that data down. As I said, it'll come down once a month. So we'll get a big slug of data once a month that will be ingested into the science pipeline at NASA Ames.
All right, we're going back to the phone bridge right now with Lewis Smith from the Times of London.
Hi, I don't mind who answers this, but I'm just trying to understand better how one camera manages to look at 100 million stars in one go. How does it work with the pixels?
Well, the focal plane consists of a large number of charge-coupled devices of the same general type that you have in your one-shot camera, only instead of the detector being the size of your thumbnail, this detector is a square foot in size. So the scale of it is very large. So you add up all the pixels of all the CCDs that are mosaic together, and you get about 95 million pixels. So what we do is use the CCD as a visible light camera, but instead of bringing full images down, as I said, we just bring down the parts of the image around each of the target stars. There are millions of stars in this field of view, but we've selected 100,000 that are particularly interesting stars to search for planets around. And those are the parts of the image that we bring down to the Earth.
All right, going back to the phone bridge, we have Mr. Barodelli from Science Now.
Hi, I know this would be jumping a gun, and I'm not sure who would answer this, but I'm curious. What happens if the data starts coming in and you get an unambiguous hit of a mirror Earth? What happens then?
I'm pretty sure we celebrate. We are specifically designing this mission to look for Earth-like planets and Earth-like orbits around Sun-like stars. That drives the design of the experiment and the hardware. What would you do? Would you declare victory?
I would be a typical scientist, and I would doubt it until we confirmed it. Mm-hmm. Then we would go to NASA headquarters, we would show them their evidence, we'd show the team the evidence, and they would help us decide whether it's appropriate for us to announce this, because we don't want to have false discoveries. We want to be very, very sure that when we say it's an Earth, it really is an Earth.
And this is an aspect of trying to make very difficult measurements that we're trying to be very careful when we make an announcement about a discovery that it's essentially bulletproof. And that's why we spend all this time with the follow-up observations to make sure the result is validated.
All right, we're going back to the phone lines once again with Mike Swift from San Jose, California.
Hi. You guys talked earlier about finding a continuum of types of planets from, gas giants like Jupiter down to terrestrial-sized planets. But within the terrestrial-sized planets, will you also be able to find a range of candidates? I mean, will you be able to find planets as small as, say, Mercury or some of the smaller rocky planets in our solar system?
What limits us is generally the noise that we see. The stars make noise, the instrument makes noise. But if we have stars that are very quiet, as quiet as the sun, and we have planets that show us lots of transits means you're in an inner orbit, then those build the signal up, and we bring the signal out of the noise because there's so many transits. Our calculations show us we should certainly be able to find Earths, almost certainly find Mars-sized planets in that condition, and it's conceivable that we might even find Mercury-sized planets.
Can I follow up and just say that, this is going to be a lot easier around the M-dwarf stars because they're not only is the habitable zone closer and therefore the orbital period is shorter and you get more repetitions, but also the star itself has a smaller radius. And so for a given planet, you block out, a larger fraction of the light. And then at the same time, again, the second part of the detection, the radial velocity follow-up, will also do the same thing that Bill Barucki has described. We're going to be, working hard to take many, many observations to try and pull up a weak signal out of the noise. So it's going to be tough, but exciting.
I don't think you promised, though, to find a Mercury for me.
Probably not a Mercury.
All right, just a reminder, the microphones are open at our NASA centers as well as here at the studio here. We have a question here from Seth. Go ahead, Seth.
Seth Borenstein, AP. Forgive me if this was asked. I was stuck on the subway. Can you go through the lower limits? I mean, you talked about maybe getting a Mercury size. What is the size of which you just can't go smaller than? And also, in terms of closeness to the star, is there a limit on how close you can detect or how far? I'm just trying to sort of get the box of the size of planets you can detect. And then the other question, I'll follow up after.
Certainly, when it comes to orbit periods, people have found planets that have orbital periods less than a day, and we certainly can find that. Since we need a confirmation, that's easy if the orbital planet's short. But if we're talking about orbital periods, say, of a couple of years, then you need a mission that runs 6 years. And right now our mission is designed to do 3.5. So we expect there will be some limit at which we can no longer detect planets with 3 transits. The other aspect of that is the noise level. We know there's always noise in the instrument, the star is fluctuating, and so we have a threshold. The threshold is the detection limit is about 7 sigma, 7 times the noise level of the period of the duration of the transit. So it has to be at least that big. So if you've got a quiet star, you can find small planets. If you've got a very noisy star, you can only find the biggest planets. But we do expect to find a lot of big planets because they will give us that 7 sigma detection that we need. The signal will be big enough for us to see it, recognize it, and be sure it's real.
So with a quiet planet, what's the smallest you could see?
I think what we've said is that we have a good chance of finding Mars-sized planets and a possibility of finding a Mercury-sized planet.
That's the lower limit?
That's the lower limit. We don't believe we can do better than that.
All right, we're going back to the studio here, auditorium.
Chimes from Voice of America Radio. I think a lot of people are going to wonder if you're talking about Earth-like planets. Well, the defining characteristic for most people is that there's life on Earth. Is there any way you'll be able to tell whether a planet that seems Earth-like in its orbit, etc., is actually capable of supporting life?
Deborah?
Okay, well, this is my chance to say that I see Kepler as a component of a whole continuum of missions, right? The radial velocities took the very first step and showed us that planets even existed around other stars. Kepler, by virtue of the statistics that it finds, is going to tell us how frequent the occurrence of Earth-sized, Earth-mass planets are. And then that's going to tell us what the next step should be. So I think from Kepler itself, no, we don't get that information about whether or not there's life there, what the atmosphere is like, or anything else. The goal, right, the 15-year, 20-year vision of astronomers, and I would bet of NASA, is to someday take a picture of a pale blue dot orbiting a nearby star. And to decide how you're going to do that and find out if there's an atmosphere on that planet and signatures of life, you've got to know what the frequency is so that you can decide, how do you what's the thriftiest way to get to that point? What kind of a mission do you build next? But there's no question that this is going to be a key driver, right? The frequency of Earths that are found by Kepler are a key driving point for NASA missions to ultimately do exactly what you're asking about, to find out whether there's life or signatures of life on other planets.
And I can echo that. This is why I call Kepler our planetary census taker. We're going to get the